Invisible bullets are flying through you right now. They are not made of metal, but of raw cosmic energy, zipping through the void at nearly the speed of light. These are the universe's most energetic particles, a mysterious rain from the depths of space that has puzzled scientists for over a century. Today, we are going on a journey to understand these ghostly travelers, and I promise you 50 mind-blowing facts that will completely change how you see the empty sky. We will uncover where they might come from, how a single particle can carry the punch of a baseball, and why their secrets might rewrite the laws of physics. What cosmic mystery has you staring up at the stars? That rain of cosmic energy has a name, and it is one of science's great misnomers. Fact number 1, cosmic rays are not rays at all. They are not beams of light or gentle waves. They are solid pieces of matter, tiny bullets of atomic debris hurtling through space. Most of them are single protons, the bare, positively charged heart of a hydrogen atom. Others are the complete nuclei of heavier elements like helium, carbon, or even iron, stripped of their electrons. What makes them extraordinary is their speed. They travel at a staggering fraction of the speed of light, carrying unbelievable energy from events we can scarcely comprehend. So when we talk about cosmic rays, we are really talking about a relentless, invisible hail of atomic shrapnel, the fastest and most energetic pieces of matter we have ever detected. This is the fundamental nature of our mystery, a particle storm that has been bathing our planet since long before humans walked the Earth. This historical blunder begins with a man and a balloon. Fact number 2, the name cosmic rays is a century-old accident, a label born from a brilliant misunderstanding. In the early 1900s, scientists were puzzled by a persistent background radiation in the air. They assumed it came from the ground, from radioactive rocks, but an Austrian physicist named Victor Hess had a daring idea. He would take his sensitive instruments up far above the Earth to see if the radiation decreased. Between 1911 and 1913, Hess made a series of perilous balloon flights, ascending to altitudes over 5 kilometers, a feat of incredible bravery at the time. What he discovered was the opposite of what everyone expected. The radiation did not fade away, it grew stronger the higher he went. The source was not below but above, pouring in from the depths of space. Hess concluded these were penetrating rays of some kind, a new form of high-energy electromagnetic radiation from the cosmos. He called them cosmic radiation, and the name, though incorrect about their true particle nature, simply stuck. His courageous flights earned him the Nobel Prize and opened humanity's eyes to a hidden, energetic universe raining down upon us, even if we got the name wrong. But how fast is this cosmic hail actually moving? Fact number 3 reveals the true scale. These particles are the speed demons of the cosmos. While light, of course, holds the ultimate speed record, the most energetic cosmic rays come breathtakingly close. We are talking about velocities of 99.999999999999999% of the speed of light. That is not a typo, that is 29s after the decimal point. At that unimaginable speed, a single proton could circle the entire Earth more than 7 times in just 1 second. From our human perspective, a particle traveling that fast experiences time almost standing still. A journey across our 100,000 light-year wide galaxy, which would take a beam of light 100 millennia, would feel like just a few years to the particle itself. This is not just fast, it is physics pushing, reality warping speed. It means these tiny specks of matter are carrying so much raw kinetic energy that they become, in a very real sense, the fastest lumps of stuff in the entire universe. And that sheer, unbelievable velocity is the source of their terrifying power, a power we have only begun to measure. That staggering speed gives these particles an almost timeless quality. Fact 4. Some cosmic rays are ancient messengers, relics from the dawn of time itself. While many come from recent, violent events in our galactic neighborhood, a portion of these travelers have been on an epic journey since the universe was young. They have been streaking through the void for millions, even billions of years. Imagine a single proton accelerated by some cataclysm in a galaxy so distant its light has long since faded, set on a course that would one day intersect with a tiny blue planet. For eons, it travels undisturbed through the near-perfect vacuum of intergalactic space, a silent bullet from a forgotten war. When such a particle finally strikes our atmosphere, it is not just delivering energy, it is delivering a message. Encoded in its type, its energy, and its trajectory is a fossil record of the conditions that created it. By studying these ancient arrivals, scientists can peer back into cosmic history, learning about the elemental furnaces of early galaxies and the magnetic landscapes of the vast cosmic web. Each one is a time capsule, a piece of a puzzle that helps us understand how the universe built itself from primordial simplicity into the complex, structured cosmos we see today. What stories could a billion-year-old proton tell? The sheer age of these particles is humbling, but their energy is what truly shatters our understanding. Fact 5 brings us to the most legendary cosmic ray ever recorded, a particle so absurdly powerful it earned the nickname the Oh My God particle. On the 15th of October 1991, a detector at the Fly's Eye Observatory in Utah registered a single, solitary proton hitting our atmosphere. This was not unusual in itself, but the energy it carried was beyond anything science could explain. This one tiny subatomic particle possessed the kinetic energy of a professionally thrown baseball. Think about that for a moment. A baseball weighing about 5 ounces, hurled at nearly 100 miles per hour, carries a significant punch. All of that force, all of that energy, was packed into a speck of matter a million times smaller than a grain of sand. The numbers are almost comical. This proton hit with an energy of 300 exaelectron volts. To put that in human terms, it was about 40 million times more powerful than the protons we smashed together in our largest particle accelerators here on Earth. The existence of this single particle created an immediate and profound mystery. According to our best theories, nothing in our own galaxy is powerful enough to accelerate a proton to such an insane speed. Its origin point, based on its trajectory, seemed to be an empty patch of space, devoid of any known cosmic powerhouse like a supernova or a black hole. The Oh My God particle did not just break records, it broke the rules, challenging physicists to explain what kind of cosmic catastrophe could possibly serve as its gun. The Oh My God particle forces us to confront a scale of energy that defies all intuition. Fact 6. The power packed into these ultra-high energy cosmic rays is simply beyond anything in our daily experience. We have already compared one to a baseball, but let us break that down even further. A single proton, one of the smallest things we know of, can carry the kinetic energy of a bullet fired from a rifle. The most extreme examples, like that legendary particle, contain the energy of a brick dropped from a rooftop or a tennis ball served by a professional. Think about the machinery needed to give a tennis ball that much speed, the muscles and the racket and the precise motion. Now compress all that force into a fundamental speck of matter smaller than an atom. This is not just a little bit of energy, it is a monumental, concentrated fury. To achieve this on Earth, we need machines like the Large Hadron Collider, a 17-mile underground ring costing billions of dollars, just to accelerate protons to a tiny fraction of this cosmic power. And yet, the universe does this naturally, flinging these atomic bullets across galaxies with ease. It is a humbling reminder that the forces at play in the depths of space operate on a level so far beyond our planet-bound engineering that they might as well be magic. What kind of cosmic accelerator could possibly be that powerful? This leads us to the great enduring mystery, fact number 7. Where do these cosmic bullets actually come from? For over a century, this has been the central puzzle. We know they are here, we can measure their incredible energy, but tracing them back to their source is like trying to find the specific gun that fired a single bullet found in the middle of an ocean. For the lower energy cosmic rays, we have strong suspects. The shockwaves from exploding stars, supernova remnants, are fantastic natural particle accelerators, capable of whipping protons up to tremendous speeds. We also look to the violent hearts of distant galaxies, where supermassive black holes create jets of matter and radiation, phenomena known as active galactic nuclei. Even the colossal explosions known as gamma-ray bursts are potential factories for these energetic particles. Yet, for the most extreme cosmic rays, the ones like the oh my god particle, all these suspects seem insufficient. Their energy is simply too high. They should not be able to travel vast distances without losing power to collisions with the faint cosmic microwave background radiation, the leftover glow from the Big Bang. This creates a paradox. If they come from far away, they should have faded. If they come from nearby, we see no suitable cosmic powerhouse in that direction. Their origins remain a blank spot on our map of the universe, a signature from an engine of destruction so powerful we have not yet learned to see it. The universe's most powerful particle accelerators are not built by human hands. Fact 8. For most of the cosmic rays that fill our galaxy, the prime suspect is a titanic, beautiful death, a supernova. When a massive star exhausts its nuclear fuel, its core collapses in a heartbeat, triggering an explosion so bright it can outshine an entire galaxy. The real magic for cosmic rays happens in the aftermath. The blast flings an expanding shell of stellar debris outward at thousands of kilometers per second, creating a colossal shockwave that ripples through the surrounding space. This shockwave is a natural and brutally efficient particle accelerator. Imagine a magnetic trap, a region of tangled magnetic fields riding the leading edge of this expanding fireball. A lone proton drifting in the interstellar gas can get caught in this turbulent zone. It bounces back and forth, trapped between the approaching shock front and the magnetic turbulence behind it. With each crossing, it gains a little more speed, like a surfer being pushed repeatedly by a perfect wave. Over hundreds or thousands of years, this process can whip a simple proton up to nearly the speed of light, until finally, the magnetic cage can no longer hold it. The particle escapes, shot into the galaxy like a bullet from a cosmic rifle. A single supernova remnant can act as a factory for billions upon billions of these particles, continuously manufacturing the cosmic rays that eventually rain down on planets like ours. In a very real sense, we are constantly feeling the reverberations of stellar cataclysms that happened long ago and far away, their energy echoing through time and space. But that supernova bullet does not fly straight to Earth. Fact 9. Our galaxy is not an empty highway for cosmic rays. It is a twisting, turning magnetic maze. The Milky Way is threaded with an invisible web of magnetic fields, generated by the motion of charged particles and the churning of interstellar gas. These fields are weak by Earth standards, but they are vast, stretching across thousands of light years. For a cosmic ray, especially one at lower energies, this is like trying to sprint through a hall of mirrors while being pushed by unseen hands. The charged particle, whether it is a proton or an atomic nucleus, does not travel in a straight line from its source to our detectors. Instead, it gets caught in this magnetic web, spiraling along the field lines in a chaotic corkscrew path. A particle that started its journey from a supernova in one part of the galaxy might be deflected, twisted, and redirected countless times over millions of years before it finally, by pure chance, plunges into our atmosphere. This is the core reason why pinpointing the origin of most cosmic rays is so maddeningly difficult. By the time we detect one, its incoming direction tells us almost nothing about where it began. The magnetic fields of the galaxy have thoroughly scrambled the cosmic signal, erasing the return address on the message. We are left with a mystery delivery, knowing something incredible happened somewhere out there, but with the map to find it hopelessly smudged. That magnetic maze means we rarely meet a cosmic ray in its original, pristine form. Fact 10. The spectacular event we actually detect from the ground is not the lone traveler, but its explosive final act, a phenomenon known as an extensive air shower. Picture that single, ultra-fast proton, after a journey of perhaps millions of years, finally reaching the thin veil of our atmosphere. It does not quietly slip through. Traveling at nearly the speed of light, it smashes directly into the nucleus of a nitrogen or oxygen molecule miles above the Earth's surface. The collision is catastrophic, a miniature recreation of the particle-shattering violence inside our largest accelerators. The proton and the atomic nucleus disintegrate in a flash of energy, producing a spray of new secondary particles, pions and kaons, and other exotic fragments. These new particles, still carrying immense energy, immediately race onward, only to collide with other air molecules themselves, creating another generation of particles. This process repeats in a blindingly fast chain reaction, a multiplicative cascade that spreads out like an inverted, growing tree. Within microseconds, a single cosmic bullet transforms into a vast, disc-shaped front of billions upon billions of secondary particles, electrons, photons, and muons, all screaming toward the ground at relativistic speeds. This is the extensive air shower, an invisible firework display spanning kilometers. Our ground-based detectors do not catch the original cosmic ray, they catch the expanding wavefront of this particle tsunami. By studying the pattern and timing of this shower's arrival across an array of sensors spread over a wide area, scientists can work backwards like forensic detectives to calculate the energy and the type of the single, original particle that started it all from the depths of space. The silent sky is alive with these silent, constant detonations, a testament to the unseen violence raining down upon us every second. Detecting that silent cascade of particles requires a net of truly continental proportions. Fact 11 introduces the world's largest cosmic ray observatory, a scientific instrument of staggering scale. Nestled on the vast Pampa Amarilla, the high plains of Argentina, lies the Pierre Auger Observatory. Its mission is to catch the rarest and most energetic of these cosmic visitors, the ones like the Oh My God particle, events so infrequent they might only strike a single square kilometer of Earth once per century. To have any hope of catching them, you need to watch a colossal area constantly. The observatory's solution is both elegantly simple and breathtakingly vast. It is an array of 1,600 individual detector stations, each one a pristine tank filled with 12,000 liters of ultra-pure water, spread across 3,000 square kilometers of arid land. That is an area larger than Luxembourg or about the size of Rhode Island. These tanks are spaced 1.5 miles apart in a triangular grid, creating a giant, sensitive skin for our planet. When the particle front of an extensive air shower sweeps over the array, charged particles like electrons and muons zip through these water tanks faster than light can travel in water. This creates a faint blue flash of light called Cherenkov radiation. Each tank's sensors capture this flash, recording its precise timing and brightness. By combining the data from hundreds of tanks hit in a single, microseconds-long event, scientists can reconstruct the entire air shower in exquisite detail. They can determine the energy, the direction, and even the type of the original cosmic bullet that started it all from millions of light years away. This is not a telescope pointing up, it is an entire landscape listening down, transforming a remote Argentine plain into a single, giant ear tuned to the universe's most violent whispers. While the Pierre Auger Observatory watches for the particle cascades from above, another, even more elusive messenger from the cosmos requires a detector of a different kind buried deep within the Earth itself. Fact 12. To catch the universe's ghosts, we had to build a telescope out of a cubic kilometer of Antarctic ice. This is the Ice Cube Neutrino Observatory, and its target is not the cosmic rays themselves, but their neutral, ghostly cousins, neutrinos. Neutrinos are fundamental particles with almost no mass and no electric charge, which makes them the ultimate cosmic escape artists. They can fly straight through planets, stars, and entire galaxies without a single interaction. This also makes them incredibly difficult to catch, but if you can catch one, it is a priceless prize. Unlike charged cosmic rays, neutrinos are not deflected by magnetic fields. They travel in perfectly straight lines from their source, carrying an unaltered map back to the most violent places in the universe. To detect even a handful of these phantoms, scientists needed a massive, perfectly clear detector, shielded from other cosmic noise. Their solution was the pure, ancient ice at the South Pole. They drilled 86 holes over a mile deep into the glacial ice and lowered into them 5,160 sensitive light sensors, creating a grid that encompasses a full cubic kilometer of ice. When a rare neutrino from deep space does finally interact with an atom in this ice, it produces a secondary particle called a muon that moves faster than light can travel through the frozen medium. This creates a faint blue cone of light called Cherenkov radiation, the same phenomenon seen in the water tanks of Auger. The grid of sensors captures this fleeting blue flash, allowing physicists to trace the neutrino's path back to its origin in the distant cosmos. IceCube is not looking down or listening out. It is using the entire Earth as a shield, turning our planet into a giant lens to focus on the silent, straight-line signals from cosmic catastrophes no telescope can directly see. This ghostly signal from the ice leads us to one of the most bizarre characters in our cosmic story. Fact 13 introduces the neutrino, the universe's ultimate ghost particle. While cosmic rays are the heavy artillery, neutrinos are the silent spies, slipping through any barrier without a trace. They are fundamental particles, but unlike the protons that make up cosmic rays, neutrinos have almost no mass and carry no electric charge whatsoever. This makes them fantastically antisocial. A neutrino can fly through a light year of solid lead, a wall over 6 trillion miles thick, and have a 50-50 chance of coming out the other side completely unchanged. Their interaction with normal matter is so vanishingly rare that it borders on the miraculous when one does get caught, and yet they are everywhere. Right now, as you listen to this, trillions upon trillions of neutrinos from the sun and distant cosmic events are streaming through your body every single second. They are passing through the floor, through the walls, through the entire Earth as if it were not even there. This total lack of interaction is what makes them so valuable. A neutrino detected here on Earth carries an untouched, straight-line map directly back to the violent heart of its birth. A perfect cosmic clue that charged particles, twisted by magnetic fields, can never provide. Our most reliable source of ghost particles is the very heart of our solar system. Fact 14. The Sun itself is a prolific neutrino factory, and these solar neutrinos are a direct beam of sunlight from its core. Every second, deep within the Sun's fiery heart, hundreds of billions of nuclear fusion reactions are taking place. Hydrogen nuclei are crushed together under immense pressure and temperature to form helium, releasing the energy that makes the Sun shine. But that light, the photons we see and feel, takes a tortuous journey to escape. A photon born in the core might bounce around for 100,000 years, colliding with countless atoms before finally reaching the surface and streaming out into space. Neutrinos, however, are born in those same fusion reactions, and they play by different rules. The moment a neutrino is created in the solar furnace, it simply leaves. It does not interact, it does not bounce, it does not delay. It flies straight out of the Sun at the speed of light, completely unimpeded. Just 8 minutes later, that particle, carrying a direct fingerprint of the core's nuclear processes, arrives at Earth. This means that when we detect a solar neutrino, we are not seeing light from the sun's surface. We are receiving a pure, unaltered sample of its deepest, most secret heart. For decades, scientists used these ghostly messengers to test our fundamental understanding of how stars work. The number and type of neutrinos we detected matched the predictions of our stellar models with breathtaking precision, confirming that we truly understand the nuclear engine that powers our sun and, by extension, every star in the sky. It is a profound connection, a whisper from the center of a star, caught in a block of ice or a tank of cleaning fluid, telling us we got the basic story of starlight right. Those solar neutrinos are a steady stream, but the cosmos sometimes sends a sudden, screaming pulse. Fact 15. The first time humanity truly caught a ghost from a dying star was in February of 1987. On the 24th of that month, 3 neutrino detectors on Earth, separated by thousands of miles, registered something extraordinary. Over a span of just 13 seconds, they recorded a total of 24 of those elusive particles. This was not the sun's steady hum. This was a sharp, unmistakable shout from deep space. The detectors Kamiok and in Japan, the IMB in the United States, and Baksan in the Soviet Union all saw the same brief spike. Hours later, astronomers in Chile turned their telescopes to a familiar patch of sky in our neighboring galaxy, the Large Magellanic Cloud, and saw it. A new, brilliant point of light had appeared, supernova 1987A. The explosion of a blue supergiant star had just become visible from Earth. But the neutrinos told the real story. They had escaped the collapsing stellar core at the moment of cataclysm, racing ahead of the shockwave that would eventually rip the star apart and create the visible flash. Those 24 ghost particles had traveled for 168,000 years, arriving at our planet hours before the light of the explosion could fight its way out. For the first time in history, we did not just witness a stellar death, we felt its birth pang. We captured the very first breath of a supernova, a direct signal from the instant a star's heart gave way. That tiny burst of 24 neutrinos marked the dawn of an entirely new field, neutrino astronomy, proving we could use these ghostly messengers to witness the universe's most violent moments in real time. While solar neutrinos are a steady whisper, the universe also broadcasts screams. Fact 16. The detection of high-energy astrophysical neutrinos reveals a violence that dwarfs our sun. These are not the gentle messengers from a nearby star's core. These are ghost particles carrying energies millions, even billions of times greater, forged in the most extreme environments imaginable. The Ice Cube Observatory in Antarctica made this monumental discovery, not by catching a handful, but by identifying a diffuse fog of these ultra-high-energy neutrinos constantly raining down on Earth. Their staggering power points directly to cosmic particle accelerators of almost unimaginable ferocity. The prime suspects are objects like blazars, the hearts of distant galaxies where a supermassive black hole is actively feeding. As matter spirals into the abyss, it can be funneled into jets of plasma and radiation that shoot out at nearly the speed of light, pointed almost directly at Earth. Within these relativistic jets, protons can be accelerated to the energies needed to create cosmic rays. When those protons collide with other matter or light within the jet, they produce pions, which then decay into both gamma rays and these high-energy neutrinos. For the first time, IceCube provided the crucial link. By tracing the path of a single, particularly energetic neutrino back to its origin, scientists pinpointed a blazar 4 billion light-years away, actively flaring at that exact moment. This was the smoking gun. That ghostly particle was the direct, undeniable evidence that these monstrous black hole engines are not just shining brightly. They are actively manufacturing both the cosmic rays and the neutrinos that fill the cosmos. It confirmed that we are finally learning to read the universe's most energetic messages, written in the straight lines of ghosts from its darkest hearts. The ghosts from blazars are one signature of cosmic violence, but there is an event that makes even those monsters seem tame. Fact 17. Gamma-ray bursts are the single most powerful explosions in the universe since the Big Bang itself. In a span of seconds, a single burst can release more energy than our Sun will emit over its entire 10 billion-year lifetime. For that brief, blinding moment, it outshines every star in its entire galaxy combined. These are not slow, expanding fireballs like supernova. They are focused beams of pure, lethal energy, concentrated into narrow jets that scream across the cosmos at nearly the speed of light. If one were to happen in our own Milky Way and its beam were pointed directly at Earth, the effects would be catastrophic, stripping our atmosphere and ending most life on the planet. Thankfully, they are exceedingly rare in any given galaxy, and the beams are so tightly focused that the vast majority shoot harmlessly into the void. But what could possibly cause such an unimaginable detonation? The leading theories point to the most dramatic births in the cosmos. One type, the long-duration bursts lasting more than 2 seconds, are thought to be the death cries of the most massive stars, collapsing directly into black holes. As the star's core implodes, it launches these relativistic jets that drill through the outer layers of the star and blast into space, creating the gamma-ray signal we see. The other type, short-duration bursts, are likely the result of 2 ultra-dense neutron stars spiraling together in a final, fatal dance. When they finally merge, they can form a black hole in an instant, releasing a similar but shorter flash of focused energy. These cataclysms are not just spectacular light shows. The same relativistic shockwaves that produce the gamma rays are perfect engines for accelerating particles to insane energies. Many scientists believe that gamma-ray bursts are prime candidates for creating the very highest energy cosmic rays and neutrinos, the universe's ultimate bullets and ghosts forged in the brightest, most violent births imaginable. These focused beams of annihilation bring us to a specific, terrifying class of cosmic engine. Fact 18. Blazars are essentially particle beam cannons aimed directly at our planet. Imagine a supermassive black hole, millions of times heavier than our Sun, sitting at the very heart of a distant galaxy. As it voraciously consumes the gas, dust, and even stars swirling around it, the incredible forces at play do not just make matter vanish. Some of that infalling material gets twisted and channeled into 2 narrow, opposing jets that blast outward from the black hole's poles at nearly the speed of light. These jets are made of plasma, a soup of charged particles and radiation, accelerated to energies that defy comprehension. A blazar is simply the name we give to this setup when one of those deadly jets happens to be pointed right at Earth. From our perspective, it looks like a single, impossibly bright point of light, outshining every other star in its own galaxy. And it flickers violently across the entire electromagnetic spectrum, from radio waves to gamma rays. This is not a gentle glow. It is the direct, blinding glare of a relativistic blowtorch, a continuous beam of the universe's most energetic particles and photons, fired across billions of light years with our solar system in the crosshairs. Because that jet is pointed straight at us, the particles within it have a clear, unimpeded path. Scientists are now certain that the turbulent shocks within these jets are some of the most efficient particle accelerators in existence, capable of whipping protons up to the energies needed to create the ultra-high-energy cosmic rays we detect. Furthermore, when those accelerated protons collide with light or other matter inside the jet, they generate the high-energy neutrinos that observatories like IceCube capture. A blazar is not just a suspect, it is a confirmed cosmic arms dealer, actively manufacturing both the bullets and the ghosts, and for a fleeting moment in cosmic time, its weapon is trained directly on us. This unbroken beam from a blazar highlights a fundamental cosmic roadblock. Fact 19. Even the most energetic particles face a universal speed limit, a barrier known as the Grison-Zatsepin-Kuzmin cutoff. This is not a limit on how fast they can go, but on how far they can travel without being stripped of their power. The entire universe is filled with a faint, cold bath of light, the cosmic microwave background radiation. This is the afterglow of the Big Bang, a relic from when the universe was just a hot, dense soup. It is everywhere, a sea of low-energy photons that has been cooling for over 13 billion years. For a proton traveling at the absolute highest energies near the speed of light, this quiet background is not so peaceful. From the proton's perspective, these low-energy photons are massively blue-shifted, appearing as a barrage of high-energy gamma rays. When one of these photons smashes into the ultra-fast proton, something remarkable happens. The collision is so violent it can create new particles, specifically a pion. This process robs the proton of a significant chunk of its precious energy. Over a long enough journey, say from a distant galaxy to our own, this constant, slow drain adds up. It means that a proton starting with an energy above a certain threshold, about 60 exa-electron volts, should be gradually whittled down by the time it reaches us. According to the theory, we should never see a cosmic ray from a distant source with an energy higher than this GZK cutoff. It is a cosmic filter, a rule written into the fabric of space itself, ensuring that only particles from relatively nearby sources, or those that started with truly unimaginable energy, can ever hope to reach Earth with their extreme power intact. This theoretical wall makes the detection of particles like the "oh my god" particle even more perplexing, for if it came from far away, it should not exist at all. The GZK cutoff is a firm cosmic rule, but nature loves to break the rules. Fact 20. We have detected particles that should not exist, cosmic rays with energies soaring far above the predicted limit. The "oh my god" particle was just the first of several such anomalies. These are protons or atomic nuclei that arrive at Earth carrying energies of 100, 200, even 300 exa-electron volts, a realm of power that, according to our best models, should have been drained away by the cold glow of the cosmic microwave background over distances greater than about 150 million light-years. Their very existence presents a stark and thrilling puzzle. It forces two radical possibilities onto the table. The first is that these ultra-high-energy bullets are coming from sources relatively close to our own galactic neighborhood within a cosmic stone's throw. But when we look in the directions they seem to come from, we find no obvious monster, no brilliant quasar or cataclysmic explosion powerful enough to be the culprit. The second, and even more profound possibility, is that our understanding of particle physics at these extreme energies is simply incomplete. Perhaps protons traveling that fast interact with the background radiation in ways we have not yet predicted. Maybe there are exotic, unknown particles involved, or our models of the cosmic microwave background itself need revision. Each of these anomalous detections is not just a data point, it is a crack in the foundation of our knowledge, a hint that the universe's most powerful accelerators are hiding in plain sight, or that the laws governing matter at its absolute limits have secrets we have yet to uncover. That invisible rain may be doing more than just creating particle showers in our sky. Fact 21. Cosmic rays might be quietly pulling the strings of our planet's climate. This is one of the most controversial and fascinating ideas in atmospheric science, the hypothesis that these energetic particles from deep space could influence cloud cover and, by extension, global temperatures. The theory is elegant in its simplicity. When a cosmic ray, particularly a lower energy one, smashes into a molecule in the upper atmosphere, it creates a cascade of charged particles, ions. These ions can act as seeds or nucleation sites around which water vapor can condense. In theory, more ions could lead to more microscopic cloud droplets, which could coalesce into more clouds. And clouds are Earth's thermostat. Low, thick clouds reflect sunlight back into space, cooling the planet. High, thin clouds can trap heat, warming it. If the cosmic ray flux changes, the argument goes, it could alter cloud formation and change our climate. The sun plays a crucial role here. Our star's magnetic field acts as a shield, deflecting many cosmic rays away from the inner solar system. When the sun is more active with a stronger magnetic field, fewer cosmic rays reach Earth. According to the hypothesis, this should mean fewer ions, fewer clouds, and a warmer planet. When solar activity is low, more cosmic rays get through, potentially seeding more clouds and cooling things down. This proposed link offers a tantalizing explanation for historical climate shifts that seem to correlate with solar cycles, suggesting the universe's weather might subtly influence our own. But does the data hold up? The scientific community is deeply divided. While some laboratory experiments and observational studies have shown that ions can enhance the formation of ultra-fine aerosol particles, the leap from that to a globally significant effect on cloud cover is immense. Many other factors dominate cloud formation, from atmospheric temperature and humidity to the abundance of dust and pollution. Reproducing a clear, undeniable signal in the complex chaos of Earth's climate system has proven extraordinarily difficult. Critics argue that any observed correlation is weak or coincidental, overshadowed by the overwhelming forcing of greenhouse gases. This debate is far from settled. It sits at the thrilling intersection of particle physics and planetary science, a reminder that our world is not an isolated bubble. We are part of a dynamic solar system, bathed in a river of stellar and galactic energy, and untangling whether the cosmos whispers to our climate remains one of science's great detective stories. The debate over cosmic rays and our climate is a long-term puzzle, but for astronauts venturing beyond Earth's protective shield, the danger is immediate and personal. Fact 22. Cosmic radiation is one of the most serious and unsolved hazards of human spaceflight. Here on the surface, we are cocooned by two formidable defenses. The first is our atmosphere, a blanket of gas 70 miles thick that acts like a bulletproof vest, causing incoming cosmic particles to shatter harmlessly in extensive air showers high above us. The second is Earth's magnetic field, a vast, invisible force that deflects and traps many charged particles, channeling them toward the poles to create the auroras. An astronaut in low Earth orbit, like on the International Space Station, is partially protected by the magnetic field, but they still receive a radiation dose about 10 times higher than on the ground. The moment a spacecraft leaves that magnetic bubble entirely, as on a journey to the Moon or Mars, the exposure skyrockets. Outside this protective magnetosphere, astronauts are immersed in the full, unfiltered rain of galactic cosmic rays and occasional torrents of solar particles. This is not a minor concern. Each of those high-energy nuclei can act like a microscopic cannonball, tearing through delicate human cells, damaging DNA, and significantly increasing the lifetime risk of developing cancer. NASA and other space agencies treat this as a fundamental limit on mission duration, a ticking clock that counts down an astronaut's safe time in deep space. But the danger is not just a statistical future risk, it is something astronauts can actually see and feel in the moment. Many report sudden, unexplained flashes of light in their vision, even with their eyes closed. These are not hallucinations, they are the direct result of a single cosmic ray or a trapped energetic particle striking the retina or the visual cortex of the brain, causing a tiny burst of light perceived as a streak or a star. Imagine floating in the silent blackness of space and seeing a silent spark ignite inside your own head, a visceral reminder that you are swimming in a sea of atomic shrapnel. For the pioneers who will one day walk on Mars, this invisible barrage represents a constant, silent threat that must be solved, a wall of energy standing between humanity and the stars. That silent threat to astronauts has a much closer, more mundane cousin that affects us all. Cosmic rays are not just a problem for deep space, they are a quiet, persistent nuisance for the very technology we rely on every single day. Fact 23. Cosmic rays can and do cause electronic glitches in everything from airplanes to your smartphone. The primary culprit is not the original high-energy cosmic ray itself, but a secondary particle it creates. When a cosmic ray strikes the upper atmosphere, it produces a shower that includes a flood of neutrons. These subatomic particles, having no electric charge, are ghostly penetrators. They can slip through an airplane's fuselage, through the walls of a data center, and even through the microscopic circuitry of a computer chip without leaving a trace until they strike the heart of a memory cell. Inside a modern microchip, data is stored as tiny electrical charges in microscopic capacitors, representing the ones and zeros of binary code. If a stray neutron from a cosmic ray shower happens to slam into the silicon lattice of that chip, it can dislodge atoms, creating a burst of electrical charge in the wrong place at the wrong time. This momentary spike can flip a single bit of memory from a 1 to a 0, or vice versa. This is called a single event upset. It is not a permanent hardware failure, but a transient software error, a digital hiccup injected from outer space. The consequences range from the barely noticeable to the catastrophic. In a personal computer, it might cause a single pixel to flicker in a photo, or trigger a rare, unexplained system crash that you blame on bad software. In an airplane, these upsets can cause navigation systems to display erroneous data for a split second, requiring redundant systems to cross-check and correct. For satellites orbiting high above the protective atmosphere, the bombardment is constant and severe, a major design challenge that requires special radiation-hardened chips. Even on the ground, as our chips have shrunk to atomic scales, they have become more vulnerable to these invisible strikes. Large data centers for banks or cloud services now have to account for this cosmic noise in their error correction protocols, knowing that a certain number of bit flips are inevitable, a gentle but persistent rain of cosmic static into the heart of our digital world. It is a humbling thought that a chain of events starting with a dying star 100,000 light-years away can, minutes later, cause a single incorrect calculation in a spreadsheet on your laptop, a tiny, silent echo of stellar violence in the machine. The silent static in our computers is a gentle echo, but cosmic rays can leave a far more permanent mark on the world. Fact 24. These energetic particles are natural nuclear reactors in the sky, capable of triggering atomic transformations right here in our own atmosphere. When a high-energy cosmic ray, often a proton, slams into the nucleus of a stable atom in the upper air, the collision is so violent it can shatter that nucleus apart. This process, called spallation, sprays out a shower of nuclear fragments, including free neutrons. These newly liberated neutrons are the key. A neutron with no electric charge can drift along until it gently bumps into another atom and gets absorbed. If that atom is a common, stable nitrogen-14, something magical happens. The absorption of the neutron makes the nucleus unstable. To regain stability, it spits out a proton. In that instant, the atom has changed its very identity. A nitrogen atom with 7 protons has been transmuted into an atom with 6 protons, which is carbon. But not just any carbon. This new atom has 8 neutrons instead of the usual 6, making it a heavier, unstable version called carbon-14. This radioactive isotope is created continuously, high above us, in a grand alchemy driven by the cosmic rain. It then mixes into the carbon dioxide of the atmosphere, is absorbed by plants through photosynthesis, and enters the food chain, ending up in every living thing on Earth. From the moment an organism dies, it stops taking in new carbon-14, and the clock starts ticking. The isotope decays at a known, steady rate. By measuring how much carbon-14 remains in an ancient piece of wood, cloth, or bone, scientists can calculate precisely how long ago that organism lived. Radiocarbon dating, the revolutionary tool that lets us peer into human history and prehistoric climates. is powered directly by nuclear reactions sparked by cosmic bullets from distant stars. The age of the pyramids, the timeline of the last ice age, the authenticity of a priceless painting, all are read from a clock set ticking by the universe's most energetic particles. That cosmic clockwork in the sky is rewriting human history. Fact 25, the carbon-14 created by cosmic rays is the ultimate timekeeper for our planet's recent past, a tool of cosmic archaeology. Every living thing on Earth, from the tallest tree to the smallest insect, is built from carbon. As plants grow, they absorb carbon dioxide from the atmosphere, and animals eat those plants, incorporating that carbon into their own bodies. A tiny, constant fraction of that atmospheric carbon is the radioactive carbon-14, freshly minted by cosmic ray collisions. For as long as an organism is alive, it maintains a perfect equilibrium with the atmosphere, its level of carbon-14 staying constant. But the moment it dies, that intake stops, the cosmic clock starts. From that instant, the unstable carbon-14 atoms begin to decay, transforming back into stable nitrogen at a perfectly predictable rate. Scientists call this a half-life of 5,730 years. This means that after that amount of time, exactly half of the carbon-14 in a sample will have vanished. After another 5,730 years, half of what remains will be gone, leaving only a quarter of the original amount, and so on. By meticulously measuring the minuscule amount of carbon-14 left in an ancient artifact, a piece of charcoal from a prehistoric hearth, a scrap of linen from an Egyptian tomb, a bone from a Neanderthal campsite, researchers can calculate with remarkable precision when that organism stopped living. This technique, radiocarbon dating, has a reach of up to about 50,000 years, a window that encompasses the entire story of modern humanity. It has settled fierce debates, proving the Vikings reached North America centuries before Columbus, accurately dating the Iceman Ötzi to over 5,000 years ago, and building a reliable timeline for the rise and fall of civilizations across the globe. It is a profound connection, a direct link between the nuclear fury of distant stars and the quiet chronology of our own story. The age of a wooden tool, the authenticity of a sacred relic, the timing of a mass extinction. These are all questions answered by counting atoms forged in the upper air by bullets from the cosmos. That cosmic clock ticks on Earth, but to truly measure the universe's reign, we had to send a listener beyond the sun's protective reach. Fact 26, humanity's farthest messengers, the Voyager probes, gave us our first direct taste of the raw, unfiltered cosmic sea. For decades, these twin spacecraft traveled through the heliosphere, the vast bubble of charged particles and magnetic fields blown outward by the solar wind. Within this bubble, the sun's influence acts as a partial shield, deflecting and modulating the incoming torrent of galactic cosmic rays. Then, in 2012, Voyager 1 did something historic. It crossed the boundary called the heliopause, the final frontier where the pressure of the solar wind gives way to the true interstellar medium. The moment it pierced this invisible wall, its instruments registered a dramatic and unmistakable change. The intensity of galactic cosmic rays, those high-energy particles from distant stars and cataclysms, suddenly surged by nearly 100%. It was as if the probe had stepped from a sheltered porch into a raging storm. Voyager 2 followed suit 6 years later, confirming the discovery. This was not a model or a theory anymore. It was a direct measurement, a hard number sent back from the void, proving that the sun's protective bubble is real and that outside it lies a far more intense bath of cosmic radiation. The Voyagers, now silent ambassadors drifting in the darkness, delivered a critical piece of the puzzle, showing us the true strength of the galactic gale that our star so diligently holds at bay. Even as Voyager measured the raw storm outside, our detectors on Earth were mapping its structure. Fact 27, the cosmic ray energy spectrum is not a smooth slope. It has distinct telling features known as the knee and the ankle. Plot the number of cosmic rays arriving against their energy on a graph, and you see a steep, steady curve. Lower energy particles are common, like a gentle drizzle. As the energy climbs, they become exponentially rarer, a downpour thinning to a few heavy drops. But then, around 10 to the power of 15 electron volts, the curve makes a sharp bend. This is the knee. Suddenly, the number of ultra-high energy particles drops off even more dramatically than before. It is as if the cosmic supply chain hits a limit. Scientists believe this bend marks the maximum power output of our galaxy's own particle accelerators, likely the shockwaves from supernova remnants. Within the Milky Way's magnetic maze, even the most efficient stellar explosions seem incapable of pushing protons beyond this energetic threshold. The curve continues its steep plunge into even rarer territory until around 10 to the 18 electron volts, something changes again. This is the ankle. Here, the spectrum subtly flattens out, suggesting a new population of particles is beginning to dominate. These are the true monsters, the ones with energies so high they could not have been confined by our galaxy's magnetic fields for long. The ankle is thought to be the transition point, where the local galactic drizzle gives way to an intergalactic downpour. Beyond this energy, the cosmic rays raining down on us are likely born in far more violent extragalactic engines, the cause of active galaxies, colliding galaxy clusters, or perhaps the still mysterious sources of the oh my god particle. The knee and the ankle are not just data points, they are signposts in a vast, invisible landscape, telling us where one cosmic regime ends and another, even more ferocious one begins. Those signposts in the energy spectrum are deciphered through the silent explosions constantly detonating above us. Fact 28. The extensive air shower is not just a spectacle, it is a cosmic detective's most valuable tool. By meticulously reading the pattern of debris that reaches the ground, scientists can perform a breathtaking feat of reverse engineering, reconstructing the energy, mass, and even the direction of the single, original particle that started it all miles overhead. The shower arrives not as a uniform wave, but as a structured front. At its core, racing ahead, are muons. These heavy cousins of the electron are penetrating and stable, often reaching the ground directly. They form the dense, central heart of the shower footprint. Surrounding this core is a broad disk of electrons and positrons, created from the decay of other particles, and a spray of photons, the gamma rays from the cascade. The precise layout of this particle rain on the ground tells the entire story. The lateral spread of the shower, how wide the disk of particles is, reveals the altitude of the first collision. A wider spread means the primary cosmic ray hit higher in the atmosphere, giving the shower more room to develop. The total number of particles that hit the detector array is the direct key to the original energy. More particles mean a more energetic primary. It is a simple, powerful equation written in a million tiny impacts, but the most clever clue comes from the ratio of different particles. The number of muons compared to the number of electrons is a sensitive fingerprint of the primary's identity. A heavy atomic nucleus, like an iron atom, will produce a shower rich in muons. A lightweight proton, on the other hand, creates a shower with far fewer. By counting these different messengers, physicists can determine if the bullet from deep space was a single proton, a helium nucleus, or a heavier piece of stellar shrapnel. From a fleeting flash of light in a water tank or a burst of signals across a desert plain, they rebuild the cosmic crime scene, revealing the nature of a visitor that traveled for eons to die in our sky. Among the myriad particles in that cosmic cascade, one stands out for its sheer persistence. Fact 29. Muons are the heavy, penetrating workhorses of the extensive air shower. Think of them as the electron's burly, short-lived cousin. They share the same negative electric charge, but a muon is around 200 times more massive. This extra heft is the key to their remarkable ability. While electrons and photons in the shower are quickly absorbed by the air, muons, born high in the atmosphere from decaying pions, barrel straight down with formidable momentum. They are so penetrating that they can travel kilometers through solid rock, reaching deep underground, even passing through the entire Earth with only a slight reduction in numbers. For physicists, this penetrating power makes them a crucial diagnostic tool. The muon count in a shower reveals the nature of the primary cosmic ray, acting as a fingerprint for its mass. But their ability to slip through matter has also inspired a brilliant and practical application, muon tomography. Just as doctors use X-rays to see inside the human body, scientists can now use these natural cosmic particles to peer inside massive, dense structures. By placing detectors around an object like a pyramid, a volcano, or a nuclear reactor, and meticulously mapping the paths of millions of muons as they pass through, researchers can create a three-dimensional density map. A void inside a pyramid, a rising magma chamber in a volcano, or hidden cracks in concrete containment walls all reveal themselves as subtle shadows in the cosmic rain. We are turning the universe's own radioactive fallout into a new kind of vision, using particles born in stellar cataclysms to uncover secrets buried deep within our own world. This ability to see through solid rock with cosmic particles has unlocked hidden chapters of human history. Fact 30. Muon tomography is turning the pyramids of Egypt into open books. The technique is as elegant as it is powerful. By placing an array of sensitive muon detectors in known chambers, like the descending corridor of the Great Pyramid of Giza, and leaving them there for months, scientists can map the density of the millions of tons of stone above them. Remember, muons rain down constantly from the sky. Where the stone is thick and dense, fewer muons get through. Where there is a void, an open space, more muons pass unimpeded. By patiently counting the muons arriving from every angle, a detailed density map, a cosmic X-ray, slowly comes into focus. In 2017, this is exactly what an international team did. Their detectors revealed a stunning anomaly, a large, previously unknown void deep within the pyramid's heart above the Grand Gallery. This chamber, dubbed the Big Void, is at least 30 meters long and has the same cross-section as the Grand Gallery itself. Its purpose remains a complete mystery. It could be a structural relief chamber, a hidden repository, or something entirely unforeseen. For over 4,000 years, this secret space existed, utterly inaccessible and invisible to every radar scan and camera probe. It took the silent, relentless rain of particles from exploded stars to finally expose it. Muon tomography does not stop at archaeology. The same principle is used to peer into the throats of active volcanoes like Mount Vesuvius, mapping the rising magma to better predict eruptions. It can inspect the thick concrete containment domes of nuclear reactors for hidden cracks or erosion, all without taking a single brick apart. We are learning to use the universe's background static as a flashlight, illuminating the dark, dense places of our world with the ghostly afterglow of cosmic violence. The same ghostly particles that reveal hidden chambers may hold the key to the universe's greatest secret. Fact 31. Cosmic rays and neutrinos could be our first direct signal from the invisible cosmos, the long-sought signature of dark matter. For decades, astronomers have known that most of the universe's mass is missing. Galaxies spin too fast and clusters of galaxies bend light too strongly to be held together by the gravity of the stars and gas we can see. The only explanation is an enormous amount of unseen matter, a mysterious substance that does not emit, absorb, or reflect light. We call it dark matter, and it makes up about 85% of all matter in the cosmos. But what is it? We have no idea. We only know it is there by the gravitational pull it exerts on everything else. The leading candidate is a hypothetical particle known as a weakly interacting massive particle, or WIMP. As the name suggests, these particles would be heavy but interact with normal matter only through gravity and the weak nuclear force, making them nearly as ghostly as neutrinos. This is where the cosmic connection gets thrilling. If dark matter is made of WIMP, then it should be everywhere, including in a vast halo surrounding our own Milky Way galaxy. And wherever dark matter particles concentrate, there is a chance they could occasionally collide and annihilate each other or spontaneously decay. Either of those processes would release a burst of energy, producing a spray of standard model particles we know how to detect, like gamma rays, protons, antimatter, and crucially, neutrinos. So imagine a scenario. A detector like ice cube buried in the Antarctic ice registers a sudden, unexplained spike of high-energy neutrinos coming not from a blazar or a supernova, but from the dense center of our own galaxy, or from the heart of the sun where dark matter could have become gravitationally trapped. Or a space telescope picks up an excess of gamma rays with a specific energy signature from a region dense with dark matter. That signal would not be a message from a star. It would be a whisper from the shadow universe itself, the first tangible piece of the dark matter puzzle. This makes cosmic ray and neutrino observatories not just telescopes for violent events, but potential microscopes for the fundamental nature of reality. Every unexplained bump in their data, every anomalous particle that does not fit an astrophysical source, is scrutinized as a possible clue. The hunt is on, a silent fishing expedition in the cosmic sea, where the ultimate prize is not just understanding where the universe's energy comes from, but what most of it is actually made of. But the dark matter hunt is not our only search for cosmic ghosts. Fact 32, the cosmic rain includes particles of antimatter, the mirror image of normal matter. Within the cascade of an extensive air shower, detectors have found the unmistakable signatures of positrons, the antimatter counterpart to electrons, and even antiprotons. Finding them is like finding a left-handed glove in a world where everything else is right-handed. These antimatter particles are not just theoretical curiosities, they are real, physical objects arriving from space. Their presence is a profound clue because antimatter is notoriously fragile. In our universe, dominated by normal matter, an antiparticle survives only until it meets its corresponding particle. When that happens, they annihilate each other in a flash of pure energy, vanishing completely. So, for these cosmic antimatter messengers to reach us at all, they must have been created relatively recently and nearby, in places where they could escape annihilation and fly freely through the void. This points to two thrilling possibilities for their origin. The first is from exotic astrophysical objects like pulsars. These rapidly spinning neutron stars have immense magnetic fields that can accelerate particles and create matter-antimatter pairs in their violent surroundings. The second and more tantalizing possibility is dark matter. If dark matter particles are indeed WIMP, their mutual annihilation would naturally produce a spray of standard particles and their antimatter opposites. Finding an excess of antimatter, particularly at specific energy ranges, could be the smoking gun for this invisible cosmic substance. The hunt has now escalated beyond just positrons and antiprotons. Scientists are desperately searching for the ultimate prize, anti-nuclei, like anti-helium or even anti-carbon. Creating a single anti-helium nucleus in a cosmic accelerator would require conditions so extreme and rare that its detection would almost certainly point to a process far beyond ordinary astrophysics, perhaps even the decay or annihilation of primordial dark matter from the dawn of time. Every antimatter particle caught is a message in a bottle from the universe's most extreme and secret laboratories, a potential key to unlocking the nature of the cosmos itself. Hunting for these cosmic ghosts requires the ultimate vantage point, a silent sentinel in the vacuum of space. Fact 33, the alpha magnetic spectrometer, known as MS-02, is a cosmic ray detective of unparalleled precision, bolted to the side of the International Space Station. This is not a telescope that looks at light. It is a 7.5-ton, $2 billion particle physics laboratory orbiting 250 miles above the Earth, designed to do one thing with exquisite accuracy: catch and identify the cosmic rain directly before it ever touches our atmosphere. For over a decade, its array of powerful magnets, silicon trackers, and particle identifiers has been sifting through billions upon billions of cosmic rays, proton by proton, electron by positron, nucleus by nucleus. Its position is its superpower. By operating above the atmosphere, AMS avoids the chaotic mess of the extensive air shower. It meets the primary cosmic particles in their original, pristine state, measuring their charge, their energy, and their type with a level of detail impossible from the ground. Its primary mission is to solve the antimatter mystery, to count the positrons and antiprotons with staggering accuracy, searching for any tiny excess or unusual pattern in their energy spectrum that could betray the presence of annihilating dark matter. Every anomalous bump in its data is scrutinized, every ratio of particle to antiparticle calculated to the last decimal, as it patiently listens to the whispers of the cosmos, hoping to hear the distinctive signature of the universe's hidden majority in the silent rain of atomic shrapnel. The silent rain that shaped our past may have also sparked our very beginnings. Fact 34: cosmic rays could have been the universe's strange midwife to life itself. This is not a firm conclusion, but a profound and speculative idea that connects the most violent events in the cosmos to the delicate chemistry of a living cell. Picture the early Earth over 4 billion years ago, a turbulent world of volcanoes, lightning, and a shallow, warm ocean often called the primordial soup. This broth of simple chemicals, water, ammonia, methane, and carbon dioxide, was the raw material. But raw material needs a spark, a source of energy to jumpstart the complex reactions that build the molecules of life, like amino acids and the nucleobases of RNA. We often think of lightning or ultraviolet light from the young sun as that spark. Yet there was another, more exotic energy source constantly bathing the planet, the relentless hail of cosmic rays. When a high-energy particle from a distant supernova slammed into the atmosphere or even into the shallow seas, it did not just create a light show. It produced a localized storm of ionizing radiation and secondary particles, a burst of raw energy that could break apart simple molecules and force them to recombine into more complex, even prebiotic forms. In a sense, cosmic rays could have acted as a cosmic stirrer, randomly but persistently adding energy to the pot, increasing the chances that the right ingredients would bump into each other with enough force to create something new, something that could eventually self-replicate. The universe, in its endless cycles of destruction and creation, might have been patiently injecting the seeds of complexity into our world long before the first cell divided. The universe's most energetic particles do not travel through a uniform void. We are floating inside a specific cosmic environment, a local structure that directly filters the rain of cosmic rays reaching our planet. Fact 35: our solar system resides within a vast, cavernous region of space known as the local bubble. This is not an empty void, but a roughly 1,000 light-year-wide cavity filled with extremely hot, incredibly thin, ionized gas, a plasma millions of degrees hot, yet so diffuse it would be considered a near-perfect vacuum in any laboratory on Earth. This bubble is our local interstellar neighborhood, and it shapes the very character of the cosmic rays that finally reach us. How did this colossal cavity form? The leading theory points to a chain of catastrophic events that occurred between 10 and 20 million years ago. In our galactic vicinity, a cluster of massive stars was born. These stars lived fast and died young, exploding as supernova one after another. The titanic shockwaves from these sequential stellar detonations acted like a series of cosmic bulldozers, sweeping up and compressing the cooler, denser interstellar gas and dust into the bubble's swirling walls. The energy from those blasts also heated the remaining gas inside the cavity to its present scorching temperature. This local architecture has a direct effect on the cosmic ray flux. The magnetic fields embedded in the hot plasma of the local bubble and the turbulent walls of denser material that surround it act as a maze and a filter for incoming particles. Lower energy cosmic rays, which are more easily deflected, get scrambled and modulated by this local environment. Their intensity and even their direction can be subtly altered before they finally spiral inward to our solar system. In a very real sense, the cosmic rays we measure are not a pure sample of the galactic gale. They are a local weather report influenced by the ancient, ghostly remnants of stellar explosions whose light faded millions of years before humans walked the Earth. We are living inside the still glowing aftermath of a forgotten celestial war, and its echoes are written in the particles that silently streak through our detectors. That ancient celestial war leaves its signature in a faint, ghostly glow high in the night sky. Fact 36. To catch the universe's most energetic bullets, we must sometimes watch the air itself light up. While detectors like the Pierre-Auger array listen for the particle cascade hitting the ground, other observatories use a more ethereal technique, watching the atmosphere become a temporary fluorescent screen. This is the principle behind the telescope array in the high desert of Utah, and it targets the most elusive cosmic rays of all, the ultra-high-energy ones that arrive perhaps once per century per square kilometer. Their method is breathtakingly indirect. When the particle front of an extensive air shower races through the atmosphere, the billions of charged particles, mostly electrons and positrons, excite the nitrogen molecules in the air. For a fleeting moment, as these molecules relax back to their normal state, they emit a faint ultraviolet light. This is not the bright flash of lightning, but a soft, diffuse glow that lasts only a few millionths of a second, invisible to the human eye. The telescope array uses a network of sophisticated telescopes stationed in the darkness, their mirrors and sensors tuned specifically to see this ultraviolet fluorescence. On a clear, moonless night, these telescopes do not look at stars. They stare at fixed patches of the empty black sky between them, waiting. When an ultra-high-energy cosmic ray triggers a massive air shower, the telescopes see the faint track of that ultraviolet glow moving through their field of view, like a ghostly needle stitching the atmosphere. By triangulating the signal from multiple telescopes, scientists can reconstruct the shower's axis in 3 dimensions with incredible precision, tracing it back to the original particle's trajectory through space. This fluorescence technique provides a complementary view to ground arrays, measuring the shower's development as it happens in the air, offering a second, independent way to calculate the primary particle's energy and origin. It is a silent vigil in the desert, watching for the moment the sky itself briefly whispers in ultraviolet, telling the story of a catastrophe that happened 100 million light-years away. The ultraviolet whispers in the Utah desert have begun to form a pattern, a clue written in the rarest of arrivals. Fact 37. The telescope array has glimpsed a possible source, a faint but tantalizing hotspot in the sky. After years of patiently watching for those ultra-high-energy cosmic rays, the ones with power exceeding 57 exa-electronvolts, the data from the array started to show something more than random noise. The arrival directions of these extreme particles were not scattered evenly across the heavens. Instead, a disproportionate number seemed to be coming from a specific patch of the northern sky, a region about 40 degrees wide, roughly 20 times the diameter of the full moon. This is not a pinprick location of a single star or galaxy. It is a broad swath of space, and its position is deeply intriguing. It points not to a known object within our Milky Way, but to a region just outside our galaxy's plane, in the general direction of the constellation Ursa Major. This hotspot, if it is real, suggests that the universe's most powerful particle accelerators might not be randomly distributed, but could be clustered in a specific structure in the extragalactic realm, perhaps a nearby galaxy cluster or a filament of the cosmic web. The statistics, however, are the critical caveat. The signal is built on just a few dozen of these extraordinarily rare events collected over many years. While the chance of this clustering happening randomly is small, it is not yet definitive proof. It is a compelling hint, a whisper growing slightly louder in the cosmic static. It is the kind of clue that keeps physicists awake at night, because if it holds, it means we are finally starting to trace the spray of the universe's most powerful shotgun, narrowing down the search for the engines of destruction to a specific quadrant of the cosmos. That faint hotspot in the cosmic map is a clue, but it is still a puzzle. Fact 38, neutrino astronomy is a revolution in how we see the universe, a new window opening onto the cosmos's darkest and most violent corners. For centuries, we have explored the universe using light, from the visible colors our eyes see to the radio waves, X-rays, and gamma rays our telescopes capture. But light can be blocked, scattered, or absorbed by dust and gas. Charged cosmic rays are hopelessly scrambled by magnetic fields. Neutrinos change everything. These ghost particles, born in the same cataclysms that create cosmic rays, carry two supreme advantages. First, they have no electric charge. This means the magnetic webs of galaxies, the very mazes that twist cosmic rays into confusion, have no hold on them whatsoever. A neutrino flies in a perfectly straight line from the moment it is created. Second, they barely interact with matter. They pass through entire stars, through dust clouds, through anything that would obscure or dim a beam of light. This makes them the ultimate cosmic messengers. They arrive at Earth carrying an unaltered map, a pristine return address stamped with the exact coordinates of their birthplace. When we detect a high-energy neutrino, we are not seeing a scrambled signal or a reflection. We are receiving a direct telegram from the heart of the event itself, from deep inside an active galactic nucleus, from the furious shockwave of a supernova, or perhaps from something even more exotic. For the first time, we are not just observing the universe's fireworks from the outside through a foggy window. We are catching the silent, invisible shrapnel from the explosion itself, pieces of the engine that flew straight to us. This is not an improvement on an old method, it is an entirely new sense. We have learned to see with ghost eyes. The ghost eyes of Ice Cube finally saw a face in the darkness. Fact 39, in September of 2017, a single high-energy neutrino struck the Antarctic ice with a force that would change astronomy forever. This was not just another ghost in the data. Its energy was a staggering 290 tera-electronvolts, and its arrival direction was pinpointed with unprecedented accuracy. Within moments of the detection, Ice Cube sent out an automated alert to observatories around the world and in space. This was a call to arms for a new kind of science, multi-messenger astronomy. The goal was to see if anything visible was happening at that exact spot in the sky, at that exact moment. Telescopes across the globe and in orbit, from gamma-ray satellites to optical and radio observatories, swiveled to the coordinates. What they found was a smoking gun. In that precise patch of sky, 4 billion light-years away, a known blazar called TXS 0506 plus 056 was in a state of extreme eruption. It was flaring violently, emitting a torrent of gamma rays. The timing was perfect. The neutrino had arrived during the peak of the blazar's outburst. This was the crucial, undeniable link. For the first time in history, scientists had definitively connected a ghostly, high-energy neutrino to a specific, cataclysmic source in the distant universe. It was the proof they had been searching for. That blazar's relativistic jet was not just shining with light, it was a cosmic particle accelerator of unimaginable power, actively manufacturing both the high-energy photons and the neutrinos that traveled across the cosmos. This single event marked the dawn of a new era, proving we could now use multiple cosmic messengers, light and particles together, to tell the complete story of the universe's most violent events. That single neutrino and its brilliant flare of light marked a turning point. Fact 40. We are now in the era of multi-messenger astronomy, a revolutionary way of seeing that pieces together the full story of cosmic violence. For the first time, we are not just listening to one voice from the cosmos, we are hearing a chorus. Each type of messenger brings a unique piece of the puzzle. Light from radio waves to gamma rays shows us the hot, glowing aftermath of an explosion, the fire and the smoke. Cosmic rays are the actual bullets fired from the cosmic gun, but their path is scrambled by magnetic fields erasing their origin. Neutrinos are the silent, straight-line shrapnel from the heart of the engine itself, carrying an untouched map. And now we have a fourth, even more fundamental messenger, gravitational waves. These are ripples in the fabric of space-time itself, triggered by the most massive collisions, like two black holes or neutron stars spiraling together. Each one tells a different part of the truth. Imagine trying to understand a car crash by only hearing the sound of the impact. You would know something violent happened, but not the speed, the direction, or the damage. Now add a security camera video, the testimony of a witness, and the forensic report from the skid marks. Suddenly, you have the complete picture. That is what multi-messenger astronomy does for the universe. When a gravitational wave detector like LIGO feels a tremor from a neutron star collision, telescopes around the world and in space can swivel to that patch of sky to catch the flash of light, the kilonova. Space-based observatories can then search for any high-energy gamma rays or X-rays from the event, and neutrino detectors like IceCube listen intently for any ghostly particles that might have escaped the chaos. By combining all these signals, we can finally answer the fundamental questions. What exactly exploded or collided? How much energy was released? What elements were forged in the fire? And crucially, are these events the long-sought factories for the universe's most energetic particles? This coordinated hunt transforms astronomy from passive observation into active detective work, building a unified narrative from the scattered whispers of light, gravity, and matter. It is how we are learning to read the universe's entire diary, not just a few torn-out pages. While we search for monsters in deep space, a more familiar star also fires its own volley of cosmic bullets. Fact 41. Our own sun is a source of potent cosmic rays, though of a very different breed. These are solar energetic particles, and they are born from the sun's sudden, violent tantrums. During a solar flare, a colossal explosion on the sun's surface, or a coronal mass ejection, a billion-ton cloud of magnetized plasma hurled into space, protons and electrons can get trapped in the tangled magnetic fields and whipped up to significant speeds. They do not reach the near-light speed extremes of their galactic cousins, but they pack a serious and immediate punch, arriving at Earth in a matter of minutes to hours after the solar event. This torrent of charged particles is the primary driver of what we call space weather. When a powerful wave of these solar cosmic rays washes over our planet, it does not just create pretty auroras. It induces powerful electrical currents in the ground that can overload power grids, causing massive blackouts. It can fry the sensitive electronics of satellites, turning billion-dollar assets into silent, drifting junk. It bathes astronauts in dangerous radiation, posing a severe risk to anyone outside Earth's protective magnetic shield. This is not a distant theoretical threat. In March of 1989, a coronal mass ejection triggered a geomagnetic storm so intense it collapsed the entire Hydro-Quebec power grid in Canada within seconds, leaving 6 million people in the dark for 9 hours. A storm of similar magnitude today, in our far more electronically dependent world, could cause catastrophic cascading failures. So while we marvel at the galactic gale, we must also respect the occasional solar squall, a reminder that our life-giving star also has the power to disrupt the very technological fabric of our civilization. Our planet's magnetic shield does more than just deflect, it also captures. Fact 42. The Van Allen belts are two colossal, donut-shaped zones of intense radiation that encircle the Earth, held in place by our planet's magnetic field like iron filings around a magnet. These are not solid rings, but dynamic regions of space dominated by a seething soup of high-energy charged particles, protons and electrons. Where do these particles come from? They are a captured bounty, snared from the dual streams of the solar wind and galactic cosmic rays. When these charged particles approach Earth, our magnetic field grabs them and forces them into a spiraling dance, bouncing back and forth between the magnetic poles in a matter of seconds while also drifting slowly around the planet. The inner belt, starting about 1,000 kilometers up, is relatively stable and dense with high-energy protons. The outer belt, beginning around 13,000 kilometers, is more variable, swelling with electrons during solar storms. For us on the surface, these belts are a distant abstraction, but for spacecraft they define a zone of peril. Satellites in medium Earth orbit, like those used for GPS navigation, must be designed to operate within this permanent radiation storm. Their sensitive electronics are hardened with special shielding, and their systems are built with redundancy, knowing that a single trapped particle can flip a critical bit and cause a malfunction. The belts are a constant reminder that our planet's protection is a complex, dynamic force field, one that not only guards us but also imprisons a fragment of the cosmic fury, creating a permanent radioactive moat in the sky we must learn to navigate. The captured fury of the Van Allen belts is a local phenomenon, but the cosmic rain has been quietly manufacturing elements on a galactic scale. Fact 43. Cosmic rays solve a profound cosmological mystery, the puzzling origin of the universe's lightest, rarest elements, lithium, beryllium, and boron. When we look at the elemental composition of the cosmos, a clear pattern emerges. The very lightest elements, hydrogen and helium, were forged in the Big Bang itself. Almost everything heavier than helium, from the carbon in our cells to the iron in our blood, was cooked in the nuclear furnaces of stars or in their violent supernova deaths. But three light elements break this tidy rule: lithium, beryllium, and boron. They are too heavy to have been made in significant amounts in the Big Bang, yet they are too fragile to survive the intense heat inside stars. In a star's core, these atoms would be instantly destroyed, fused into heavier elements like helium or carbon. So if stars do not make them and the Big Bang did not leave enough, where did they come from? The answer lies in the relentless, shattering power of the cosmic ray hail. Imagine a nucleus of a heavier, common atom like carbon or oxygen drifting peacefully in the vast interstellar medium. Suddenly, a high-energy cosmic ray proton, traveling at nearly the speed of light, smashes into it. The collision is so violent it literally spalls the larger nucleus apart, fragmenting it like a sledgehammer hitting a ceramic pot. The debris from this nuclear shattering includes smaller, lighter pieces, the very atoms of lithium, beryllium, and boron. This process, known as cosmic ray spallation, is a form of cosmic alchemy. It does not build atoms up through fusion, it breaks them down through catastrophic collision. The interstellar space of our galaxy is a continuous, slow-motion demolition site where cosmic rays chip away at the heavier elements, manufacturing these fragile, light elements as byproducts. Every atom of boron in a plant, every atom of lithium in a smartphone battery, was likely born not in a star's heart, but in the chaotic aftermath of a violent particle collision in the dark, cold void between the stars. It is a humbling origin story written in fragments. The sun's quiet tantrums can sometimes escalate into a full-scale cosmic bombardment. Fact 44. On very rare occasions, a solar storm is so ferocious that it breaches our atmospheric shield entirely, triggering what scientists call a ground-level enhancement. This is not the gentle increase in auroral activity or a minor radio blackout. This is the sun firing a direct volley of particles so energetic they mimic the most powerful galactic cosmic rays. In a typical solar particle event, the protons accelerated by a flare or coronal mass ejection are stopped high in the atmosphere. But during a Gili, these solar protons reach energies exceeding 1 giga-electronvolt, sometimes even 10. At that power, they do not just ionize the upper air, they plunge all the way to the surface. When they strike the denser atmosphere near the ground, they initiate their own miniature extensive air showers, cascades of secondary particles just like those from deep space. These showers are rich in neutrons which rain down upon the Earth's surface, and that is how we know a Gili is happening. A global network of neutron monitors, simple but robust instruments often housed in sheds or small buildings from the Arctic to Antarctica, suddenly records a massive spike. Their counters click wildly as the neutron flux surges by hundreds or even thousands of % in a matter of minutes. It is the unmistakable signature of the Sun in a state of extreme fury, a direct particle assault that bypasses our planet's magnetic defenses and reaches the very ground we stand on. These events are thankfully rare, occurring only a handful of times per solar cycle, but they serve as a stark reminder. Our star is not just a gentle source of light and warmth, it is a capricious nuclear reactor capable of launching a radioactive storm directly at our doorstep. That rain of neutrons from a solar storm is a temporary spike, but another cosmic particle offers a constant, quiet proof of a deeper truth. Fact 45. Cosmic ray muons are a living, breathing demonstration of Einstein's theory of special relativity, a confirmation written in the sky above us every single second. To understand why, we need to meet the muon on its own terms. Created high in the atmosphere from decaying pions, a muon is fundamentally unstable. At rest in a laboratory, its average lifetime is a fleeting 2.2 microseconds, 2 millionths of a second. In that brief flash, even traveling at the speed of light, a muon could only travel about 660 meters before decaying into an electron and a pair of neutrinos. That is less than half a mile, yet we detect them constantly here on the ground after a journey that begins over 10 kilometers up. According to the simple, classical logic of Isaac Newton, this should be impossible. The trip from the upper atmosphere to the surface should take dozens of those fleeting lifetimes. The muons should vanish long before they reach our detectors. But they do not. They arrive in their billions, and the reason is a fundamental strangeness of our universe, time dilation. Einstein's special relativity tells us that time is not a universal constant. It flows at different rates depending on how fast you are moving. For an object traveling at a significant fraction of the speed of light, time itself slows down relative to a stationary observer. These muons, born in the cosmic ray cascade, are screaming toward Earth at over 99.9% of light speed. From our perspective here on the ground, their internal clocks are running incredibly slowly. What is a 2 microsecond lifetime in their frame of reference stretches out to over 22 microseconds in ours. That is more than enough time for them to complete their descent. From the muon's own perspective, an equally mind-bending thing happens. Due to another effect of relativity, length contraction, the distance from the upper atmosphere to the ground is not 10 kilometers. From the viewpoint of a particle moving that fast, the entire Earth is rushing up to meet it, and the distance it must travel is dramatically compressed, shrinking to a length it can easily cover in its own short lifetime. So the muons reach us for two mutually true reasons. We see their time stretched and they see the distance shrunk. This is not a theoretical abstraction confined to particle accelerators. It is a real, measurable phenomenon happening in the air above your head right now. The relentless rain of muons is a continuous, natural experiment, proving every moment that the fabric of space-time is flexible, that time is relative, and that the universe operates by rules far more wondrous than our everyday intuition suggests. While muons constantly prove Einstein's theory, our next leap in understanding demands a new generation of eyes. Fact 46. the future of cosmic particle astronomy is being built right now, in the form of two colossal next-generation observatories designed to see the invisible universe with unprecedented clarity. The first is the Cherenkov Telescope Array, or CTA. This is not a single telescope, but a global network of over 100 telescopes of 3 different sizes, planned for sites in the Canary Islands and the Chilean Andes. Its target is not the particles themselves, but the faint blue Cherenkov light flashes they produce when ultra-high-energy gamma rays from cosmic sources slam into our atmosphere. The CTA will be 10 times more sensitive than any existing gamma-ray telescope. Imagine trying to listen to a symphony with cotton in your ears and then suddenly having it removed. That is the leap in sensitivity. It will map the gamma-ray sky with breathtaking detail, pinpointing the accelerators of cosmic rays with precision, watching active galaxies flare in real time, and perhaps catching the fleeting gamma-ray signature of dark matter annihilation. Its partner in this new era is KM3-NET, a neutrino telescope being built at the bottom of the Mediterranean Sea. Following the pioneering example of IceCube, KM3-NET will transform a cubic kilometer of deep, clear seawater into a neutrino detector. Instead of sensors in ice, it will use thousands of light-sensitive spheres anchored to the seafloor, looking for the same blue Cherenkov light from neutrino interactions. The Mediterranean location offers a crucial advantage. It views the southern sky, including the center of our own Milky Way galaxy. This is a prime hunting ground for neutrinos from galactic sources like supernova remnants and the potentially dense concentration of dark matter at the galactic core. Together, the CTA and KM3-NET represent a coordinated assault on the high-energy universe. One will watch for the brilliant gamma-ray flashes that often accompany particle acceleration, while the other listens for the silent neutrinos that escape straight from the engine room. By correlating their data in real time, these observatories will practice multi-messenger astronomy at a scale never before possible, building a complete dynamic picture of where and how the universe makes its most energetic particles. We are not just building bigger detectors, we are weaving a finer net to catch the whispers and shouts of a cosmos drenched in invisible power. These colossal new observatories are not just mapping the cosmos, they are stress-testing the very foundations of reality. Fact 47. The extreme energies of cosmic rays provide a natural laboratory to test the limits of physics itself, probing for cracks in our most fundamental theories. Our current rulebook for the universe, the Standard Model of Particle Physics, is a masterpiece of human understanding. It explains with stunning accuracy how particles interact, from the glue that holds atoms together to the radioactive decay of elements. But we know it is incomplete. It does not include gravity, it offers no explanation for dark matter, and it cannot account for the overwhelming dominance of matter over antimatter in the cosmos. To find what lies beyond, we need to push matter to its absolute limits, to energies so high that new, exotic phenomena might reveal themselves. Here on Earth, we build machines like the Large Hadron Collider, smashing particles together at tremendous speeds. But the universe has been running its own, far more powerful collider for billions of years. The most energetic cosmic rays are protons or nuclei accelerated to energies millions of times beyond anything our best technology can achieve. When these particles finally strike our atmosphere, that collision recreates for a fleeting instant, conditions not seen since the first moments after the Big Bang. It is a chance to see physics operating under ultimate stress. Scientists scrutinize these events for any tiny deviation from what the Standard Model predicts. One of the most profound searches is for a violation of Lorentz invariance. This is a cornerstone of Einstein's relativity, the principle that the laws of physics are the same for all observers, regardless of their speed or direction. But some theories of quantum gravity suggest that at the extreme energies near the Planck scale, this perfect symmetry might fray. Space itself might have a subtle grain to it, like wood, causing particles traveling at different energies or in different directions to move at very slightly different speeds. An ultra-high-energy cosmic ray, after a journey of 100 million light-years, could accumulate a detectable delay if Lorentz invariants were broken. By comparing the arrival times of gamma rays, neutrinos, and cosmic rays from the same distant cataclysm, we can hunt for this minuscule lag, a potential whisper from the quantum structure of spacetime. Another ghost hunters seek in the cosmic rain is the magnetic monopole. In our everyday world, magnets always have two poles, a north and a south. You can cut a bar magnet in half, and you get two smaller magnets, each with its own north and south. The equations of physics, however, suggest the possibility of a particle with only a single magnetic charge, a north without a south, or vice versa. This magnetic monopole would be a revolutionary discovery, a relic from the universe's earliest, most symmetric state. Some theories suggest that the most energetic cosmic rays might not be protons at all, but these ultra-heavy, ultra-rare monopoles plowing through the atmosphere. Detectors scan the extensive air showers for signatures that do not match any known particle, a trail of ionization too dense or a cascade that develops too slowly. Each anomalous event is a spark of hope, a suggestion that within the cosmic downpour we might find a key to a deeper, more unified theory of everything. The universe's most violent accidents are not just messages about distant stars. They are experiments conducted on a galactic scale, offering us front-row seats to physics at its absolute edge. This galactic-scale particle accelerator is not just a curiosity, it is a major player in our galaxy's energy economy. Fact 48: cosmic rays represent a significant fraction of the Milky Way's total energy budget, a hidden reservoir of power woven into the fabric of interstellar space. To understand their true importance, we need to step back and look at our galaxy's entire energy ledger. What are the dominant forces and stores of power in the vast space between the stars? First, there is starlight itself, the radiant energy pouring from billions of suns. Then there is the thermal energy of the interstellar gas, the gentle warmth of hydrogen clouds drifting in the dark. There is the immense coiled power of the galaxy's magnetic fields and the gravitational potential energy binding everything together. And then there is the kinetic energy of the cosmic rays, the silent, invisible rain of ultra-fast particles. When scientists add up all these contributions, the result is astonishing. The total energy density of cosmic rays in the Milky Way's disk is roughly equal to the energy density of starlight. It is comparable to the energy stored in the galaxy's magnetic fields, and it is about 1% of the thermal energy of all the interstellar gas. Think about that for a moment. The light from every star, from the brilliant blue giants to the faint red dwarfs, carries about the same raw power as the ceaseless motion of these atomic bullets flying in the dark. This is not a minor side effect. It is a fundamental component of our galactic ecosystem. This reservoir of particle energy exerts a constant, gentle pressure on the interstellar medium, helping to support clouds of gas against their own gravity, influencing how they collapse to form new stars. It ionizes the faint hydrogen in deep space, affecting its chemistry and how it interacts with magnetic fields. Cosmic rays are not just passive passengers or distant messengers. They are an active, energetic ingredient in the recipe of our galaxy, as essential to its dynamics as starlight or magnetism. They are the invisible heartbeat of the Milky Way, a pulse of power from dying stars that helps shape the birth of new ones. This invisible energy is the background static of the cosmos itself. Fact 49: cosmic rays are everywhere and they are constant. This is not an occasional storm, but a ceaseless, gentle drizzle that has persisted for billions of years. Every planet, every moon, every asteroid in our solar system is bathed in this same radioactive rain. Earth is not a special target, it is simply one more rocky body swimming in a galactic sea of atomic shrapnel. Long before the first single-celled organism stirred in a primordial ocean, this particle hail was already falling. It was here before the dinosaurs, before the continents split, before the moon cooled. It is the universe's oldest weather, a fossil wind blowing from the graves of ancient stars. This constancy means the energy they deposit is woven into the very fabric of our planetary environment. It is a low-level source of ionization in the air we breathe, a subtle contributor to the natural radiation that has always been part of our world. For any future human explorers standing on the silent plains of Mars or the icy surface of Europa, this same cosmic hum will be their constant companion, a reminder that no world is ever truly isolated. The universe is not a quiet, empty void. It thrums with the silent echoes of perpetual catastrophe, a background choir of stellar death singing in particles instead of light. This ceaseless cosmic hum brings us to our final and perhaps most important fact, Fact 50. For all we have discovered, the universe's most energetic particles still guard profound, unsolved mysteries. Each detection, each new piece of data, seems to open more questions than it answers. The greatest puzzle remains the source of the ultra-high-energy cosmic rays, the oh my god particles. We have found tantalizing hints like the northern hotspot, but we still cannot point to a specific celestial object and say that is the gun. What unimaginable engine, lurking in the apparent emptiness between galaxies, can fire a single proton with the force of a baseball? Is it a new type of astrophysical monster we have not yet learned to recognize, or is it a sign that our understanding of particle physics at these extremes is fundamentally flawed? Closer to home, the role of cosmic rays in our own world remains hotly debated. Do they truly seed clouds and nudge our planet's climate, weaving a subtle thread between stellar death and earthly weather? Or is their influence lost in the noise of a vastly more complex atmospheric system? And on the grandest scale, what is their ultimate role in the life cycle of a galaxy? We know they carry immense energy, but how exactly does that invisible pressure sculpt gas clouds, regulate star formation, and shape the evolution of the Milky Way itself? Finally, and most profoundly, cosmic rays and their ghostly neutrino cousins may hold the key to the universe's darkest secrets. Is the anomalous antimatter we detect a whisper from annihilating dark matter? Could the next unexplained particle in the ice or the desert be the first direct signal from the shadow universe, revealing the nature of the cosmos's missing majority? Every unanswered question is an invitation, a frontier of ignorance that calls for a new generation of detectors, telescopes, and most of all, human curiosity. The story is not ending, it is accelerating. The silent rain that has fallen for eons is still speaking, and we are only just beginning to understand its language. From the ghostly whisper of a neutrino to the thunderous arrival of a cosmic bullet, we have traced a path through the invisible architecture of the cosmos. These 50 facts are not just isolated pieces of trivia, they are chapters in a single, ongoing story of discovery. They reveal a universe that is anything but quiet and empty. It is a dynamic, violent, and breathtakingly energetic place where dying stars forge atomic shrapnel, black holes fire relativistic jets, and the fabric of space-time itself is tested by particles moving at the absolute edge of reality. Cosmic rays, neutrinos, and gamma rays are the privileged messengers from these forbidden zones, the only witnesses that can escape the heart of the catastrophe and fly straight to us, carrying their unaltered stories across the light years. This journey underscores a profound shift in how we understand our place in the cosmos. We are not passive observers on a sheltered rock. We are participants in a grand, energetic exchange. The air above us crackles with silent detonations. The ground beneath our feet is scanned by penetrating muons. Our very history is dated by atoms created in the upper atmosphere by nuclear collisions. Our technology stumbles on cosmic static, and our future dreams of space travel are bounded by this invisible radiation. We live within the echo of stellar explosions, inside a bubble carved by ancient supernova, bathed in a fossil wind that has blown for billions of years. Yet for all we have mapped and measured, the greatest revelations likely still lie ahead. The northern hotspot, the oh my god particle, the anomalous antimatter, these are not puzzles solved but clues freshly dropped. They are signposts pointing toward physics we have not yet written, toward cosmic engines we have not yet learned to see. The new generation of observatories, from the Cherenkov telescope array to the deep-sea eyes of KM3 are not just bigger tools. They are new senses allowing us to listen to the universe's chorus in ways we never could before. So the next time you look up at a seemingly quiet night sky, remember the truth. You are standing in a storm. A rain of relics and ghosts and pure energy is falling through you every second, a direct connection to the most extreme event since the beginning of time. That silent, starry void is alive with stories of creation and destruction, written in a language of particles and light. The universe is still speaking, and its most incredible messages are the ones we have only just begun to hear. Stay curious. That silent conversation between the cosmos and our curiosity depends on listeners like you. Thank you for joining me on this journey through the universe's most energetic reign. If one of these 50 facts reshaped how you see the night sky, I would love to hear about it. Tell me in the comments, was it the ancient muons proving relativity, the ghostly neutrinos from blazars, or the sheer power of a single proton carrying the punch of a baseball? What cosmic mystery keeps you staring up and wondering? If you enjoyed this deep dive into the invisible, please give this video a like and subscribe to the channel. It truly helps us continue exploring the universe's greatest secrets, bringing you more stories written in light, gravity, and silent particles. Until next time, remember this. Every clear, dark night is an invitation. When you look up, you are not just seeing points of light. You are looking into a storm of creation, a silent, energetic dialogue that has been ongoing for billions of years. You are part of the audience for the greatest show in the cosmos, so go outside, find a patch of darkness, and look up. The universe is still telling its